So for the phantom design, we selected different materials in order to simulate the soft tissue the best way possible. So in the selected materials, we selected the gelatin or granitine to simulate soft tissue. We selected glycerin to improve mechanical properties. We also selected the white vinegar to adjust the pH and the texture of the gel. And well, we did some the plastic tubing we used plastic tubing to represent the blood vessels, and we 3D printed the base. This was to hold the gel and the phantom structure for the ultrasound analysis, and some model specifications of which we did was the two vessels where we have one healthy and one with aneurysm, and the vessel location and dimensions are based on clinical examples of the healthy vessel and the sick vessel with the aneurysm. Then, with the following selected materials previously mentioned, we proceeded to build the phantom. So we follow these steps to build this phantom. First, we designed and 3D printed the base mold, which is the white one in the image. Then we made the placement of the tubing in the mold to simulate the arteries and the vessels. We prepared the gelatin-based mixture, and uh, we did the embedding of the aneurysma, dilation, and sealing. We faced some challenges while building this phantom, which was first of all we needed to avoid air bubbles. We needed to make the correct position of the tubing, and mainly we needed to prevent leaks while the water was running. So we could not they can the phantom couldn't have any leaks because of the ultrasound system. We needed to take care of that.
In this slide, we used color Doppler ultrasound to see how blood flows through the vessel. On the left, you see a healthy vessel. The color is smooth and even, and this means the blood is flowing normally in one direction and at a steady speed. Now look at the image on the right. This is the vessel with an aneurysm. You can see many colors mixed together and the flow looks messy. This shows that the blood is moving in different directions and at different speeds, which is not normal.
Using Doppler ultrasound, we evaluated blood flow through both the healthy and aneurysmal vessels. The healthy vessels show laminar flow with uniform velocity, while the aneurysmal section displayed disturbed flow patterns and variations in velocity due to the dilation. In this clip, you can observe the Doppler signal from the healthy vessel. Note the consistent waveform. In contrast, the aneurysmal vessels showed turbulence and velocity changes.
All right, let's dive into what we saw in our experiment. Starting with the aneurysmal vessel on the left, things got chaotic. The flow was messy and uneven, with blood moving at different speeds and in different directions. This is exactly what we expected in a vessel with an aneurysm because it disrupts the normal laminar flow and creates turbulence that can be dangerous to the body. Now compare that to the healthy vessel on the right. Much calmer. The blood flow was smooth and steady, just like we want it to be on a real circulatory system. Now, it is important to point out our limitations of the project. First, we didn't use a pulsatile pump. That means we couldn't fully mimic the natural heartbeat rhythm that drives real blood flow. Second, our tubing was too stiff. It didn't stretch like real blood vessels do. This rigidity affected how the aneurysm formed and how the blood flowed through it. So, while the results were insightful, they're not a perfect match for real physiology, but they give us a strong idea of how an aneurysm can seriously impact blood flow. Now, let's talk about how can we improve our experiment. First, the tubing we used was stiff. as already mentioned, real blood vessels are soft and flexible, so one improvement will be to use more elastic materials like silicone or latex. This will help the tubes to behave more like real arteries, especially when the pressure changes. Also, for the Phantom, we used gelatin, but after some time, the gelatin started to crack and break apart. So that's why we really like the example shown in the top right image, because it is a much more solid and durable Phantom. Another key upgrade will be to add a pulsatile pump. Right now, our flow is steady, but the human heart doesn't work like that. It beats. A pulsatile pump will create a heart-like flow with pulses. This will help us to see what really happens during systole and diastole, when the heart contracts and relaxes. In the diagram below, the most relevant change will be adding that kind of pump.
Yes, for sure. So, in conclusion, the phantom successfully replicate the key hemodynamic differences between a healthy vessel and an aneurysm, as seen with Doppler ultrasound. Laminar turbulent flow, velocity changes, and a wave for distortion matches a clinical patterns, confirming its value for training and basic studies. It provides to be a low-cost reproducible tool for simulating vascular issues in clearly visual way. Despite some structural limits, it offers strong base for future improvements and hands-on learning in biomedical engineering and ultrasound imaging.